So today, I'm not sure why this looks so big on today's screen. We're going to be talking, I think I'm cutting off some stuff. Yes, I am. Okay, there we go. All right, so today we're going to finish Chapter 3. We have done forward, backwards, an exhaustive subset selection. We've done stage-wise a little bit. We've done shrinkage, penalized regression, ridge and lasso. And we've talked a little bit about least angle regression, which finds the solution path there for the lasso. Today we're going to talk about principal components again. Now, I talked about principal components when we discussed the ridge penalty. In particular, that penalty was kind of a function of those principal components, and those that did not had the least variation were kind of penalized the most in that process, and that was what we wanted to do there. So we already have some basic impression about what principal components are from that discussion, and those of you that took 546 know a little bit more deeper what they are because they're used in unsupervised and supervised learning. Today we're going to be talking about them with respect to regression. And then we're going to talk about partial least squares. These, your book calls the methods that use derived input directions. They are derived because they are derived from the entire variable space. Okay, so it's different. Although we're going to be selecting, 2 principal components or 3 principal components or 5 or whatever, we're doing selection there. We're always going to select in order, by the way. We would never take principal component 1 and 9. Okay, so we are truncating the principal components, but it's not a feature selection method because actually the principal components are derived from all of the variables in the data set. Okay, so that way it still captures that data in a way that lowers the dimension. Okay, so that is what these derived inputs really mean. Okay. So let me give you a little bit of an objective, and I'm going to jump to another slide set too, just to give you a little bit more impression of the principal components. Your book really doesn't talk much about them because it's only half a page. The introduction text does a much better job with this particular topic, but they kind of save principal components for Chapter 10 when they do unsupervised learning. But I'm going to give you a little bit more information here. So the objective is to derive a reduced set of orthogonal. This is an important piece. Remember, if we have orthogonal predictors, this is important for the estimation of the regression coefficients. There's no influence from the other predictors. We want a reduced set of orthogonal linear projections of a single collection of correlated variables. Here we have our x. Okay, so we need orthogonal projections of these variables, which I say here correlated. They may be correlated. They're probably correlated a little bit because nothing is going to be exactly 0 in real data. But they might be highly correlated, which we always turn to principal component regression when we have a set of highly correlated variables because it does this orthogonalization. And it does it in such a way that the projections, these derived inputs, are ordered by decreasing variances. So it's used in a whole bunch of fields. Sometimes we have to go to this method, and there's 2 reasons why we might reach for principal components when we have to do regression. Okay? The first reason is that we have a high-dimensional data set. Okay? Maybe we have 30,000 predictors, right? We need a way to work with that, and it's not going to happen with subset selection. Okay? So we need a way to kind of get over this high-dimensional issue. That's classically like the first method that is kind of reached for. Another method, another reason, the second reason is if you have high correlation in a data set. So for example, I work with NMR data, and the NMR data is based on a spectral frequency, and it has this interesting curve. But anyways, these variables, which we call bins, are very highly correlated. Okay, so in order to break that correlation, we typically use this principal component analysis. It's also high dimensional. So sometimes you have situations where it's both or one or the other, but it's a very useful technique. It's also, so as I mentioned right now, it's used for decorrelating X, and it's been used in different fields under different names. They don't necessarily use PCA as the term, but that is what they're doing. And communications theory, atmosphere sciences, It's used all over in engineering. It can be supervised or unsupervised, which makes it a very valuable technique. Okay. Now, another thing is that aside from dimension reduction and decorrelating, which are the two things I said we would need it for, we would really reach for PCA in the supervised setting if we had those issues to deal with. There's another thing we can use it for. We can use it for discovery, okay? And this is, in particular, important if you're trying to process data. So I said that, you guys had some experience pre-processing data, and we had a few tools at our disposal. We looked at pairs plots. We looked at other things. But what if instead of in the auto data set, instead of, a dozen different variables or less than a dozen, I gave you 50, right? So what are you going to do? You're going to do pairs plots for all 50 and try to kind of track this stuff. So as the dimension kind of increases and increases, those methods don't work because it's just not practical, okay? And 50 is low. I mean, I could have 100 or 500, and then it becomes intractable. So PCA is actually a great avenue for doing data processing. And it can be used, in particular, to flag outliers, okay, to discover anomalies in the distribution of the data, identify groups and clusters, and to distinguish coordination with experimental treatment factors. Okay, there's some beautiful papers out there with respect to this problem where you might typically do a MANOVA or something like this, and if you have high dimensional data, you can do this PCA and really understand how different metabolites or genes or whatever you're looking at coordinate with the different treatment factors of the experiment. So it's very useful things, and I always encourage people to tackle some of these things in their projects. I'm going to talk a little bit about the outlier stuff today. Many of you have seen this. It's a little bit of a tangent, but I think it's important. Okay, so just to give a little motivation, this is an example I showed last semester too. It's probably one of my favorite examples, because we all understand food. It's better than showing a bunch of genes that we don't know the function of. This data set has 961 food items and different components. If you read the label of a food, you have all these different things. Here they're talking about fat and calories and carbohydrates, protein, cholesterol, weight, and saturated fat. So these are the things that are measured on each of these. You think of the rows as the different food items, and then you have all of these things that are being measured. And so dietary data actually is always analyzed with PCA. And so I happen to have a collaborator at Roswell Park that looks at flaxseed, the use of flaxseed and different health outcomes. And there, the nutritional data is so large and it's so sparse that PCA ends up being kind of the mainstream technique for that type of analysis. So the food data is interesting, and we also have them listed according to serving sizes. That's somehow standardized in this data set. This data set comes from the MMST package, which is no longer supported in R, but it's part of a book that I like to use by Eisman. So this is what the principal components look like. Okay, this is part of the package. And so what you see here, first of all, you see all of the different variables that I mentioned here. Okay? And we also see principal component 1, 2, 3, 4, 5, 6. Now, there's no mistake, there's not a coincidence that there are 6 principal components and 6 variables. Okay? That would be guaranteed, because if you think about principal components, what it ultimately is a low rank decomposition of a matrix X. Okay? So we should be able to reconstruct the matrix exactly by kind of multiplying out the principal components with the features. So we can reconstruct X exactly. So if I have this matrix X, I can decompose it into principal components. If I have 6 variables, I'm going to have 6 components ultimately. And I can put together X again exactly. So that's one of the beautiful things about principal components. Now, in our situation, we're going to be looking for a smaller number of principal components to use in a regression model. So let's say I don't want to use all 6 variables for some reason. But imagine this was 600, right? So I'm going to find a smaller number of inputs that summarize these 6 variables. And I'm going to use that. And so smaller is what is going to be our complexity parameter for the regression. We're going to be choosing the number of principal components using cross-validation or another approach. Okay, that has to be decided. But each one of these principal components is actually a function of every single variable in the data set, and it is describing the directions of the most variation, okay, with respect to x. Now notice I'm saying with respect to x. Okay, I mentioned that PCA is used in unsupervised learning and supervised learning. This is perhaps one of the downfalls, right, because I'm using x. I'm decomposing x. But there's no guarantee that the way I decompose x is going to give a model that would be a good prediction of y, because I'm not even thinking about y when I do the decomposition, okay? But in most cases it is, because if you think of different experiments, typically we try to get variation by doing different treatments and different things, so those directions should be reflected in the principal components, which is why it ends up working almost comparable to partial least squares, which I'll discuss in about 20 minutes. Okay? So what you have here is the first one, principal component 1, 2, 3, 4, 5, and 6. And you see the variance here. I mentioned it's by decreasing variance, and that is reflected in this thing. And if I think of the total amount of variance, so I'm going to take the cumulative sum there and then figure out what the total is. The first principal component explains 44% of the variation in the data. The second one, 22. The third one, 17, 11, 4, and 0.9. So depending on how conservative or not conservative you are, you might automatically say, well, let's just walk away with the first 2, okay, or the first 3. So you've cut your data set down from 6 to 3. Certainly, this one doesn't matter too much, okay? If you end up using all 6, you're exactly in the least squares solution, because as I mentioned before, you can reconstruct that matrix X exactly, and so then you're just doing ordinary least squares using the full set of principal components. So you haven't reduced the dimensionality of the problem at all, but maybe your goal was to orthogonalize, so that would still be valuable. These vectors here are called the loadings. Okay, so we're going to define these exactly. This is what it looks like. These are called scores. So remember, there were 961 different food items. There's 961 dots here. Okay, and you have the first principal component and the second one on the y-axis. Okay, so these scores are computed using essentially a projection into the principal component space of the data set X, which we'll define specifically in a few slides. But I think this motivation is important to kind of go to big picture before we get into the formulas. What you're going to see is a breaking between some of the food items. So the first principal component score is going to describe the most variation in the data set. And what we see is that those that are over here, these are cooking fats, salts and butters, egg yolk. These are pretty heavy cholesterol foods. Okay, so these are kind of in this space. And we see the high carb food is over here. And maybe we see, you know, vegetables or something over here. So you're going to see clusters of food. Okay, and the clusters of food are going to make sense. But what is the biggest difference kind of in this data set? Well, these would be considered kind of outliers, right? Because they're actually away from this cloud. Okay, that means with the first 2 largest sources of variation, these orthogonal principal components are really being driven by this difference between these saturated fats and the high carbs. Okay, and so generally when I use principal components to think about outliers, I'm looking for those that are kind of, you know, over this way. Now, these wouldn't be considered outliers in the true sense, because once I labeled them and I say, oh, well, that's butter. Oh, well, that's cooking. It's an egg yolk. Then I realize that it makes sense in the context of the data set. But sometimes what you're going to see is, oh, 318. That sample was taken out of the freezer twice, right? It was had a repeat thaw. So maybe there's something wrong with the integrity of that sample. And so that's when you start to trace different things. And so for 6 variables, you could probably kind of figure those things out. But if there were, again, 500 variables, we would want to see how these different food items or samples related in terms of each other and how they differ from each other. So there's a strong interpretation that can be delineated from this type of plot, which we call a score plot. Okay, so you'll have some practice with this. So let me give you now the, since I'm talking a little bit about the outlier stuff, I want to just pull up this slide set, which isn't mine, and I just want to show you kind of a few steps here. Because this topic is not covered in your textbook, although I think it's one of the most important topics. Oh, this is not the right one, sorry. This is a presentation. This was a presentation by a former student who really was interested in this outlier detection. And I will just introduce the general topic anyways. I won't go through his slides. But there's a whole field of analysis that centers on this multivariate data analysis with principal components to determine outliers. And it essentially has a few different ingredients. There's these things called control charts. Okay, and so if anybody's interested in this topic, it's actually quite good. I have a great book on it for a final project. And by the way, I'll be talking about final projects next week, so I know I've gotten some emails about them. So that's coming up. Control charts kind of give you an impression of how different score plots can be interpreted with respect to these outliers. And they basically think about a few different things. Hang on just a second here. View full screen. They basically use these scores, and they can draw, for example, if you draw an ellipse, a Gaussian ellipse around the center of that cloud, we can kind of figure out what's falling outside of the different confidence intervals. Okay, so we can describe a distribution around that. Another thing that they look at is the distance to model, which is exactly a situation where you would reconstruct the X matrix, and you would kind of look as you kind of add more principal components to which ones, because you have kind of a true X value, which you know from the full reconstruction, and you kind of look for the difference between your estimated value and the true value, and you're looking for those that deviate a lot. Another thing that they do is they look at the last few principal components, because the first few generally capture something biological or some true signal in the data that it was kind of intended to be used for, but the last few have important information too, and generally they're not looked at with respect to regression, but for looking for outliers, they can be very valuable because that's where the noise happens. And so generally you would expect the noise to be kind of white, and be kind of systematic, but sometimes you can see samples really breaking this distribution, and then they deserve kind of a further investigation. So these control charts are very useful for doing that. But in the end, it's always kind of looking at individual samples and trying to understand. It's kind of been flagged using this control chart. Do I want to keep it in or do I want to remove it? So you've had a little practice with this. This type of control chart work and the outlier detection using PCA allows you to do pre-processing on a massive scale. Okay, so it's an important technique. Okay, so now let's get into kind of the nuts and bolts of the method. So the general formulation. Let Z1, Z2 to Zm represent M, okay, which is less than P, linear combinations of our original predictors, and there's P predictors, okay? That is, Zm is a combination of all P predictors. Now it has our xj, which is our data set, right? We have our data x1, x2, x3 to xp in this case. So you have our original data set, and Zm is a function of all the predictors in the data set, which I already mentioned to you, okay? All P predictors, and it has this coefficient, which we're going to call phi Jm, And it's going to be, this is essentially the loading. Okay, so the loadings I showed you before are represented by these phi's. Here they just call them general constants for now. Okay, and we can fit the linear regression model. Here I've got yi, my regression model. I've got an intercept point, which I'm calling theta now instead of beta. Okay, just to kind of twist it because we're projecting the data and we're using a different domain. So I don't want to cause confusion. And I want to be consistent with your text. So here I'm going from m is equal to 1 to big M. Okay, and I'm estimating theta is going to be the regression coefficient. ZIM is going to be the principal component, okay, plus epsilon. Okay, and this is for all samples. So we are estimating a yi, a response variable, using a linear model just like we've done before, but we're doing it on a reduced set of orthogonal inputs that are derived from the original data set. Those derived inputs are the principal components. That is the z's. These are the orthogonal inputs, okay? And another thing you're going to notice here, so these are derived from all the variables in the data set, which is why I mentioned it's not a subset selection technique. Okay, it's using all of the variables in the data set to determine these loadings. However, what you'll notice here is that I'm going from m is equal to 1 to big M. Okay, so there's 2 important points here. Big M. What is big M? M is typically less than P. Okay, so if I had 6 predictors, 6 nutritional measurements, I'm going to choose a smaller amount to represent my data. Okay, if M is equal to P, we're in the least square situation, but we're using orthogonal inputs. So typically, M is less than P. It's not required. Okay, this is less than, the book says less than. It can be less than or equal to. But here it's typically less than, so we're using a reduced set. Another thing you're going to notice is the summation goes from 1 to big M, meaning that I would never take, so usually when we think about our data set, we think about these columns that represent different features in the data set. Now you're going to have another matrix that represents different principal components, Z1, Z2, Z3. So when we do kind of subset selection, we might grab age, we might grab sex or cholesterol level. Those have a specific meaning. When we work with these orthogonal components, we're only going to be moving in a sequential manner, hence the 1 to big M, okay, because that means something. Each one is a derivation of all of the features in the data set, and they represent directions of variation going from the most to the least. So it would make no sense to use some combination of them. It's always going to be sequential. Okay, so then the regression coefficients are as usual. You just do a regression model like you would before. And the constants, if the constants are chosen wisely, see here I say wisely, it can typically outperform least squares. So we're not going to discuss kind of the method of deriving these weights. That's a longer talk, which I used to give, but I'm not going to do it this semester. But coming up with the principal components can be done essentially in 2 different ways. I mentioned the singular value decomposition. That's one route. Another route is to use eigenvalues of the covariance matrix. So there's 2 different routes. Generally, the PCA is more stable when you use SVD. Okay, and actually there's 2 methods to do this in R. And one uses SVD, one uses eigenvalues. So typically I teach with the SVD method. Okay, but that's a story for a later time or your own reading. So basically you're just doing a regression model on these reduced components. So this is what it looks like. I showed this plot before. This is a plot where you have different cities. I think there's 100 different cities here. You have population and ad spending, and they're scaled. So I think it's per 1,000 or whatever, per 100,000. So you see that right away by looking at the variation of this data set, that the direction of most variation is along this axis here, and this is the second principal component here. And also you see that population and ad spending seem to be pretty related, right? I mean, I don't know what the correlation coefficient is here, but I think it looks pretty strong. Okay. So I've been mentioning that principal components actually project the data into an orthogonal subspace. So what exactly is meant by projecting the data? So in this particular example is nice because they kind of walk you through what this means. So the green line, as discussed, is the direction with the most variability in the data. The second line is the second most direction of variability that is orthogonal to the first line, right? Because these are our orthogonal components. We know that if we have orthogonal components, we're in a good spot with respect to estimating those regression coefficients. Now, projecting. If we projected, okay, if we think about these lines, if we project points, there's 100 points here onto this line, these would have the most variance over any competing line in this space. Okay, so if I drew some different lines, this line contains the most variance. Okay, and the blue line is the same idea. It contains the second most amount of variance, subject to the fact that it is orthogonal to the first. And when it comes down to projection, it essentially comes down to finding the location on the line which is closest to the point. So, you know, when we talked about residual sum of squares, we're talking about kind of finding the distance to the curve or to the line. That's essentially what that is, to the boundary. How far is this point to being classified correctly? Mathematically, it looks like this. And this is an example for this particular one. These are the loadings, and there's a mistake here. This should be phi squared. Okay, I tried to change it, but my equation editor was not cooperating. So the loadings, the square of the loadings sum to 1. Okay, and this is the loading with respect to population. So it's a different way of looking at that same chart that we saw before. You have the different variables, and if I had 10 variables, I would have 10 loadings. Okay, but we're looking here at the population minus the population mean, add minus the add mean, and this is the principal component. This is the linear combination, or the line, that leads the maximum possible variance over all possible lines. Okay, and so there's a couple things to think about. One is these points here. These are the loadings, and they can be interpreted. They have an interpretation, so we'll talk about that in a few minutes. And if I want to push a point through here, I can do that. Okay. And so this is the first one, which I wrote on the last slide, and this is the second one. They're just two lines. And this is what the projection would look like. So here, if I project all of the points, the 100 points, to the first principal component, it kind of looks like this. Okay, we're just pushing the points toward the line. Okay. And likewise, for the second principal component, I'm pushing in this direction. Okay, and the blue dot here represents the average, which is used in the formula here to compute this particular z I1. And so there's a couple of things here. So the loadings I've already kind of described, but if I take each point and project it to the principal component, what I've done is I've evaluated a score. Okay, we call that a score. Okay, the loadings and scores. So if I take 100 different points and I project them, I pass them through this equation, each one is going to have a score on the first principal component. Just like this guy has a score on the first principal component, right? The score is about 6.7. And on the second principal component, it's close to 0, okay? And this one has coordinates too, and this one too. So by pushing them through this formula, we can kind of understand what the scores are. And if you have a big score, that means something, okay? This is another plot here where we have, on the top axis here, we have the first principal component against population. And we have the first principal component against ad spending. And what you see in the first two plots up here is that there's pretty good correlation here. So the first principal component is doing a pretty good job of, it's pretty correlated with population. So it's associated with population. Population seems to be determining kind of the biggest variation in the data set. Okay, there's only two variables, right? The second one, the other plot here says the first principal component also does a pretty good job with ad spending. Okay, so it seems to be explaining quite a bit of variation. It's associated with population and ad spending. It's associated with both. There's a strong association. If I had to come up with a correlation coefficient, I would guess it's between 0.8 and 1. Okay, 0.8 and 0.95 or something like that. So they're both very strong. The second principal component, if I do the same thing and I look at the second principal component against population, which is here, now I don't really see a lot of association, right? It's very weak. Here also, with ad spending, it's very weak. Okay. So in this particular example, there's not an obvious association between the second principal component and ad spending, or the second principal component and population. So what does that mean? Well, in this silly example, because we want to visualize things, we're kind of looking to reduce the dimensionality, right? But we only have two variables, so but this is kind of saying that you're not getting much from the second principal component. Okay, it's not really capturing a lot about these two variables. It could be kind of eliminated, and probably we could get by with just one feature, which is one principal component. Okay, and this is expected because there's high correlation between population and ad spending. Okay, we saw that at the very beginning. So we can reduce it. Okay, we can kind of see that we can reduce the dimensionality of this problem. Now, generally speaking, we can't do plots like this systematically. There's things we can do to kind of determine how many features we're going to retain, and we're going to do it in a more rigorous manner. Okay. This is a plot I showed when I talked about ridge. This is called a scree plot, and I'll show you how to do this. In fact, when you use PRComp in R and you do a plot, the automatic plot that comes up is the scree plot. And different ways of looking at this, but they're saying the same thing. If I think about, this is a variable, this is a data set with 18 features, and if I kind of look, I'm looking for an elbow in the plot. Okay. So this is kind of an elbow here. I might get by with 2 features or 3 features instead of 18. And certainly I don't need these guys. Okay. Now, there's 2 ways we're going to go about doing this. I always encourage students to look at the scree plot every single time. Okay. And also to evaluate the test error. Okay, for different values of k. I think both are fundamentally important. Okay, typically they will correspond to some degree. But if you're looking at the test error and you don't see an obvious value, in other words, you might get something more rigid. Of course, things are very subject to, sample size, to the way the data is split, to how you're evaluating your test error. But this gives you information about x. And here's the other thing. This plot does not depend at all on y. Okay? So that's an important feature of this method. So understanding in general how this variation is distributed across the components is important, because it may not coincide with the test error plot. Okay? It might be something obvious. Okay, so this is just another plot here where we looked at squared bias, test, mean squared error. This is from your text. And this is PCR, and this is ridge regression and lasso. And so we know, for example, ridge regression, I forget which one is the dotted line. Ridge regression is dotted. Ridge regression is a lot like principal component regression in the sense that the shrinkage factor is a function of the principal components or the singular values. So they should be kind of related, and they are, okay? But of course, principal component regression is a discrete process. So you see kind of steps. This is the number of components. This is a shrinkage factor. It goes over a continuum. You're going to specify a grid over which lambda can be. Maybe you're going to evaluate 100 lambdas or 1,000 lambdas or maybe just 5. But you have a grid, right? A continuous grid. I mean, it's still discrete, but it's over a continuum. The number of components is a finite number. You're going to retain 1 or 2 or 3 or 4. And it's not feature selection because we see this rocky plot when we do subset selection as well. We're going to retain 1 variable or 2 variable model, but the features are all different. You might have age and sex, and then age, sex, and weight. So these are different things. Whereas in this particular plot, again, I'm emphasizing the point that these components are derived from all of the features in the data set X. But it is a discrete process, and you can kind of see your book, the Elements book, makes a big deal about saying that this is very similar to the ridge regression penalty, which is obvious by the nature of the penalty term relying on the singular values. So that's kind of the main thing here. Again, your book kind of emphasizes this point. I don't think it's as important, but I want to share this with you. So if I think about shrinkage factor, of course, there's no, it's in or out, so it's 1 or 0 when it comes to principal component regression. So you see this discrete thing. And then with ridge, it's this continuum, but they're kind of going in the same direction. They're both going eventually down. Okay, eventually will actually be to the ordinary least square solution either way. Okay, and of course this is because I showed this formula on a slide last week that we have this shrinkage factor, which is a function of the singular values. And so the singular values are ordered, right? And those that don't contribute much are going to be penalized harder. Okay, so that's the idea there. And likewise, the principal components are ordered. And those that don't contribute much are probably not going to end up in the model. In this case, these last two. Okay. So that's kind of my segue into the next piece. So I'm going to talk about 2 methods for derived inputs in this course. The second one is partial least squares regression. So one of the pitfalls of PCA is that actually it's just a low-rank decomposition of X. It doesn't care what Y is. You don't need a Y to kind of use this approach. If you use it for regression, you do, of course, but it's not going to consider it. There's nothing built into PCA that's going to consider that Y feature. So principal or partial least squares, or sometimes it's called weighted total least squares, is looking for directions that have high variance, just like PCA. So it's going to, again, look for this sequential breakdown and variation. Let's find some derived inputs that decrease in terms of the variation they explain in the data. But it's also going to seek to maximize the variation between those features that you're deriving and the response variable Y. Okay? So this sounds like a great approach, right? And why wouldn't this work better than PCA, right? It should work at least as good as PCA. This is actually viewed as being a supervised alternative to, this should be PCA, not partial least squares. So it's a supervised way of deriving a reduced set of features. PCA is an unsupervised way of deriving a reduced set of features. So one would think that PLS would have a huge advantage over PCA. In practice, that's not exactly true. So we'll talk about that toward the end. So in a nutshell, it kind of goes like this. You standardize the inputs, which incidentally you'll do for PCA too. Then we're going to consider the inner product of each xj with y. Okay, so the inner product of xj and y. And the derived input is going to be Z1, which is a summation over these size in xj. So, okay, this looks kind of weird. It looks kind of similar to PCA, but the difference, of course, is that we have this term. This term serves as a weight. Okay, it's weighting these directions in a way that if xj has nothing to do with y, it's going to be weighted down, right? It's going to be closer to 0. It has a lot to do with y. It's going to be higher. So it gives an automatic scale for these particular weights. This is what we call the first partial least squares direction. And then there's a construction where you go further and trying to figure out the second and the third. And as before, they're going to be orthogonal, but it's just going to be one more thing. Orthogonal and have high variation with this response. High coordination with the response, as determined by this weight, which is a function of the inner product. Now the construction, therefore, is weighted according to their univariate effect on y. Right? This only concerns xj. It doesn't consider any other x's. It's looking at the univariate effect of xj on y, as measured by this inner product. Okay? In the end, just like PCA, you get a series of features, and we have Z1 to Zm, and as with PCA, we're going to, if we consider all directions, we're in the ordinary least squares solution. We're not doing anything to reduce the dimensionality. We're just using a different subspace to compute the solution. So in some ways, this particular section of the book is easy because PCA and PLS are very similar in the way they function. Very similar. Their features have the same feel to them. In PCA, we're just considering x. Here, this is a supervised version of PCA in a way that considers y, and it weights those contributions according to the relationship with y as determined by this psi coefficient. So we want to find a reduced set of coefficients just like before. Your book goes through an algorithm. Oh, actually, this topic, yeah, so this is from the Elements book. And this is obviously very specific to regression, but they give you the algorithm. You standardize each x to have a mean 0, variance 1, so essentially doing a z-score. You have an intercept term, and we have an initial data set. So you're going to go from 1 to p. P is the number of features in your data set. You come up with a derived input. Okay, so you have your Zm, just like before in the formula. And this psi is computed with the inner product of the feature with y. And now we have a regression, theta hat m. Theta hat m is a function of Zm and y. This formula here is exactly like the formula that we showed when we talked about the calculation of regression coefficients when you have orthogonal inputs. So here what we have is Zm and y determining this regression coefficient and not the other z's. You update your y hat prediction, which is a function of the last prediction, plus what you might call a step or a change. Okay, the change is from adding another component. And then there's an orthogonalization step, which essentially comes down to deflating that matrix and then finding the next partially squares direction. So you're not going to be responsible for implementing such a method on your own, but I think it is useful to kind of understand the big picture, but not something that you're going to be responsible for. The output is a sequence of fitted vectors. So you're going to have different predictions, of course, depending on how many features you're including in this set. And you can also think about the retaining these partial least squares directions. Okay? So the method is actually quite different than PCA. The method for getting principal components is quite a bit different, actually. This is what we call an iterative method. Okay, so we're updating at every iteration. PCA can also be viewed iteratively, and if I decided to write the same thing for PCA, it would look very similar except without the weight from that inner product. Okay. So here's some finer points. The most important things that I've said today: methods for derived inputs are not feature selection methods. So that's a great true or false question. Okay, so methods for derived inputs, PCA, PLS, are not feature selection methods. They use the entire data set. Another finer point is that when you get to training and testing, these points have to be thought of a little bit more carefully. And it's always a common mistake. Even in the literature, it gets past reviewers. When you do training and testing with PCA especially, one has to think about, if you're using kind of the loadings and the directions from the training set, how that applies to the test set. And unfortunately, when we do PLS and PR comp, well, PR comp you'll have more control over. But PLS, it's kind of built in, so you can't really make that mistake. But for PCA, one has to be a little bit careful about that. So, in other words, when you train your model and derive the directions, it should only be determined by the training set. Should not see the test set. The test set should not influence those directions. In theory, partial least squares should be superior, right? Because it uses the response variable, and that would seemingly be important. In practice, it works about the same as PCA. Okay, there are very few situations where I've seen a huge difference between PCA and PLS. Most people would agree with me too. And which is not to say that PLS doesn't have its space, you know. There might be some examples out there, but I haven't seen them. The reason is a well-designed experiment should have features that contribute to the variation that associate with treatment. So that kind of would get tossed out using just a decomposition of X and not considering Y. Hopefully that outcome Y does associate with those major treatment factors or the major sources of variation. If it doesn't, then that would be just a strange kind of experiment there. Okay? So that's typically why it works so well. Okay. This is another picture from your book, which I think it's okay. I think we're just going to talk about the top one. So they did a simulation. They did something with correlated features, 0.5, high correlation, kind of high, modest correlation, negative 0.5 in the other direction. But let's just look at the top one in the interest of time. Basically, this is the least squares solution up here, and these are two beta coefficients. So we kind of see the least squares solution, and again, we're using two coefficients. It's a stupid thing to do because we would never need to do any of this for just two coefficients, but we need to visualize such things. So what you kind of see, best subset selection kind of overshoots the solution in the first step. It's a discrete process, right? So it's setting B2 to 0. It does overshoot the solution for beta 1. Okay, so maybe this is kind of goes this way, and then it kind of, obviously in the second step, it reduces both to 0. The lasso is a more continuous process, right, until beta 2 crosses 0 and eventually sets it to 0, right, because once it's out, it's out. Okay, once it hits 0, it's taken out of the set of features. Ridge is a continuous penalty term that does not have the characteristics where it can eliminate coefficients that cross that 0. So this is going to shrink them back, okay, but it's going to do so continuously. Eventually they'll both hit 0. But partial least squares, it's also a discrete process, and PC principal component regression is very similar to it in this particular case. And of course, they want to emphasize the point that the ridge regression solution is kind of a compromise between subset selection and principal components. Okay, they keep saying, oh, principal components in the ridge solution with that penalty term, so they just keep talking about it over and over again. So that's one thing you kind of see, it sits between there, and that's not exactly surprising. So these are the methods of in chapter 3. You're going to have some practice doing this. Once you finish these 2 labs, you should really be able to tackle your homework. So I encourage you to get kind of a head start on this. We've talked about subset selection, this discrete process. I described it as kind of ad hoc, right? We're evaluating these subsets. Of course, if you can do so exhaustively, that's great. But if you have to use a greedy search, there's no real guarantee that you're going to arrive to a good solution or the same solution using different methods. We have issues there with kind of multiple testing that you're testing subsets, nested models of the same data. So it's very criticized in the literature. The shrinkage methods are more well accepted. You've got the ridge regression, which is used probably the most widely of all the penalized regression models. And that method was designed originally to stabilize ill-conditioned matrices that are solved using least squares. So by adding this penalty term, we have that property. However, it also has this feature of doing the shrinkage to the different coefficients in the model. Lasso, the same idea as ridge, but it has a different shape to the penalty term, such that when a coefficient crosses a 0, it's eliminated from the data set, which is why it's nice, because, of course, comparing ridge in terms of advantages and disadvantages, ridge can get things really close to 0, but it never removes them from the data set. So from a practical point of view, if you hand an investigator this laundry list of coefficients, and even if you do the F-test, it sometimes can be overwhelming, whereas in Lasso actually reduces it to a smaller number, which is easier for model interpretation. Finally, today we talked about PLS and PCR. They are not subset selection methods. They are essentially looking at an orthogonal subspace of features that are derived from the original data set X. In the case of PCA, we know it can be used for supervised or unsupervised. We know that it does not depend on Y. We know that it's not subset selection also because it's a sequential addition of features of principal components to the regression model. So once you derive these features, it's just regression as usual. Okay, so I think these are the methods that are important for Chapter 3. We've also talked about a few other things. We talked about least angle regression. You're not going to be responsible for that. Your book goes into some deeper topics that relate to Lasso, primarily because they're the authors of Lasso. I think they tend to emphasize that a little bit more. And as you do your reading, you'll notice there's this character in the book that kind of has his hands to his face, like with a scream. Those are more, you don't have to read those sections. That's like a warning. You don't have to read those sections. So that concludes what I want to say about Chapter 3. And now I've got 20 minutes left.